Okay, good afternoon, students. So welcome back to the fourth session, all right, of the Chemistry Olympiad Round 2 training. All right, so today we'll be actually studying a new homologous series in organic chemistry, which is the halogenoalkanes. Now, as the name suggests, these contain halogens inside. The part alkane obviously suggests they probably come from an alkane. So the simplest halogenoalkane would be this. Sorry. Right? So this is one of the halogenoalkanes. Okay? Now, obviously, this is called chloromethane because it only contains one carbon atom. Therefore, it's called methane. So it's chloromethane. Now, how would you make chloromethane? So previous lesson, we learned about free radical substitution of alkanes. So alkanes, like methane, can react with chlorine to produce chloromethane. Okay, now halogenoalkanes are very, very, very useful homologous series. In fact, they are the most versatile homologous series that can allow you to form many, many things, as we will see together today. Okay, so halogenoalkanes are actually very, very, very helpful. So I hope you recognize that today. All right, Ken? Now, halogenoalkanes have something special, which is, of course, they have a halogen. Now, halogens are like fluorine, chlorine, your group 7 elements. The group 7 elements tend to be electronegative. So what that means is that chlorine, it's probably going to be delta minus, whereas carbon is delta plus. So what we can say is that the carbon is electron deficient. Okay, so the carbon atom is electron deficient in a halogenoalkane. Okay, now so carbon is delta plus and electron deficient. This means that this is going to attract something else that has a negative charge. Naturally, right? A delta positive carbon will attract something that is negatively charged. The simplest thing that I can think of right now is OH minus. So if I have OH minus together with chloromethane, what will happen is, of course, this. OH minus can now share its electron pair with carbon. Right? But we know carbon is unable to form more than 4 bonds. So if oxygen wants to form a bond with carbon, but carbon already has 4 bonds. So one of the existing covalent bonds has to break. Is the covalent bond broken going to be CH or CCl? So if you look at the bond energies, the CCl covalent bond is weaker. So the CCl covalent bond breaks. And what you get, as you can imagine, is this. The CH remains intact, but what you now have is, of course, an OH that has been substituted into the halogenoalkane. Where did the Cl go to? Cl came out. And remember, the arrows have been drawn to Cl. That means the electron pair shared originally now both go to Cl. So you form Cl minus. So what do you see? You have gone from chloromethane to this molecule on the right-hand side. That's called methanol. So this is how you convert from a halogenoalkane to an alcohol. So halogenoalkanes can be converted to alcohols. All right. Now, obviously, this requires OH minus. So where did the OH minus come from? So in the lab, how do you provide OH minus hydroxide? The most common form of OH minus in your lab is just aqueous sodium hydroxide, right? So by adding aqueous sodium hydroxide to your chloromethane, you would have OH minus present. Now, this also requires reflux. You must heat with reflux. The main reason why you need reflux is because obviously chloromethane or halogenoalkanes in general are quite easily vaporized. They evaporate very, very quickly. So it is important to actually heat it with reflux, just like alcohols. Okay? Ken? So this is the first type of reaction that halogenoalkanes will undergo. Halogenoalkanes react with aqueous sodium hydroxide with reflux to form the alcohol. Now, this reaction mechanism has a name. Clearly, this is substitution because the OH had substituted chlorine away. But it's nucleophilic substitution because this OH minus is electron rich. The electron rich OH minus is attracted to the carbon, which is delta plus. Things that are electron rich are called nucleophiles. They like the nucleus. The nucleus is positive, right? So they like positive things. So things that like positive things are called nucleophiles. So OH minus is a nucleophile. That's why this mechanism's name is called nucleophilic substitution. It involves the substitution of atoms by nucleophiles. Now, is OH minus the only thing that is electron rich and a nucleophile? Obviously not, right? I'm sure you know by now, things that are electron rich typically will have a negative charge. I can easily think of other atoms which have a negative, other ions, sorry, with a negative charge. So take, for example, the next one. Cn minus. Oh my God. Okay, CH3, Cl. Okay, I'm sure you can predict what will happen next. Cn minus, obviously negatively charged. Negatively charged, electron rich. Electron rich, nucleophile. So the Cn minus is a nucleophile that will form a bond with the delta plus carbon. Chlorine is also delta minus, like just now. So the CCl covalent bond breaks. And this forms a new molecule here. Okay, so Cn contains a C triple bond to N. Okay, so this is how it works. Now this molecule on the right is called a nitrile. Nitriles contain Cn, triple bond. So this is how you go from halogenoalkane to a nitrile. Now, so obviously, how do you supply Cn, right? So just now OH minus, you use NaOH. Cn, you can also imagine, you can use a similar concept. All right, you can use NaCN. Okay, Na plus, Cn minus. However, more commonly, we use the potassium salt, potassium cyanide. Okay, KCN is called potassium cyanide. And we dissolve it in ethanol. Okay, we don't use water to dissolve it. Ethanol makes the reaction a little bit better. Okay, and this forms a nitrile. So we usually use KCN in ethanol and reflux. Now, why form the nitrile? You might think, oh, how is this even like useful, right? Just now, if you recall from the lesson just now, we talked about step down, right? So cracking, fermentation are step down, right? We also talked about reactions like hydrogenation, where the number of carbon remains the same. But let's just look at this. If I were to use Cn minus as a nucleophile to attack your halogenoalkane, your final substituted product, do you realize that it now has one more carbon than before? Your nitrile will always have one more carbon than before. This means that this is a step up reaction. So just now I mentioned, right? Oh, we don't know how to do step up yet, because this is how you do step up. To do a step up reaction, you need to use KCN in ethanol on a halogenoalkane. And this is how you achieve a step up when you form the nitrile. Now, the nitrile on its own obviously is not super duper useful. You don't usually use it for a lot of things. But this nitrile can undergo a variety of reactions, and we'll just look at one of them today. Okay, we can reduce the nitrile, okay, using lithium aluminium hydride. Now, lithium aluminium hydride is a common and very powerful reducing agent. Okay, it contains Li plus and AlH4 minus. So the AlH4 minus is the reducing agent. So we use lithium aluminium hydride, and it's dissolved in dry ether. You must dissolve the lithium aluminum hydride in dry ether. Now, why must it be dry? The reason is because lithium aluminum hydride is so powerful a reducing agent, okay, it can react with water. And it reacts very, very violently with water. So if there's just a tiny trace of water in it, it will go up in flames. Right? Lithium aluminum hydride must be handled very, very carefully. It's a powdery solid that you can dissolve in different solvents, but never with water. It must be dry ether. In fact, lithium aluminum hydride is so dangerous that even your test tubes and conical flasks must be dried overnight in an oven before you do this experiment. Okay, so when I was in university, when I did this experiment, I have to first dry all my glassware. Test tube lah, conical flask must all dry overnight first. If there's just a little trace of water, the whole thing will burn. All right. Now, after you use lithium aluminum hydride, typically you will need to, after that, okay, at the end of the reaction, you add water to react away lithium aluminum hydride carefully. Okay, you cannot have lithium aluminum hydride left behind, okay? You must add water carefully, chop by chop, okay? And what this does is that it reduces the nitrile. When the nitrile is reduced, it forms this. Oh my God, why do I keep writing C today? So it forms this, which is the amine. Amine means it has an NH2 group. Okay. Okay, so besides Cn minus, OH minus, these are negative ions, we could also think of things which are not negatively charged, but they have electrons. Take, for example, ammonia. Ammonia is NH3. NH3 has a lone pair, right? If you draw a dot and cross diagram of NH3, nitrogen has 2 electrons which are not being shared with hydrogen. So this is called a lone pair. If there's a lone pair of electrons, it's also electron rich, which means that, again, it's a nucleophile. It does the same thing. Okay, so what is formed? So this is the first step. Obviously, this will not last for long. The N doesn't want to be a positively charged, so you form this. Okay, forms HCl. The H and the Cl combine together, form HCl. So what do you look at this? Oh, again, there's an NH2, right? NH2 is an amine. Then you might think, oh, does it mean it's step up? Let's count together. There's one carbon at the start, one carbon at the end. So this is how you go from halogenoalkane to amine. But there's no step up. There's no step up if you don't use KCN. There's only step up if you use KCN. So what is this? This is just adding ammonia as a nucleophile. The ammonia substitutes the chlorine. Okay? Can. So obviously, where does the ammonia come from? How do you get ammonia? Ammonia obviously is a gas. Okay? Now, ammonia can be dissolved though. So you can dissolve it in water. But typically, we would dissolve it in ethanol. You notice like KCN just now, we also use ethanol. This one, we also use ethanol. Excess ammonia in ethanol, heat in sealed tube. Okay? So typically, we will heat this in a sealed tube to ensure that the ammonia is as concentrated as possible and doesn't escape, because ammonia tends to also vaporize quite easily. Okay? So this is the third type of nucleophilic substitution on chloromethane. Okay, so looking at what you have copied down basically how a nucleophilic substitution on a halogenoalkane results in the formation of different things, right? So you've covered 3 different types of things. Okay. Now, obviously, you can imagine just based on these 3 things, I'm able to form quite a few things. Number 1, finally, you know, wow, how do you go from halogenoalkane to an alcohol? Simple reaction. 2, how do you go from halogenoalkane to a nitrile? Simple reaction. And from a nitrile, you can go to an amine with step up. Nitrile very useful because you can step up. Useful. Okay. Finally, you have learned how to go from halogenoalkane directly to the amine, but no step up. Okay. Now let's go back to the nitrile. The nitrile can be reduced to form the amine. That's one reaction. Right? This is reduction to form the amine. Now, nitriles can also be used to form the carboxylic acids. Okay. Now, nitriles themselves, they are quite useful because you can actually use it to form the carboxylic acid. Now, the nitrile shown here can be used to form ethanoic acid. And all you need for this reaction is dilute H2SO4 reflux. By adding a little bit of H2SO4 in and reflux it, after some time, you form the ethanoic acid. So this is how you go from nitrile to the carboxylic acid. We've stepped up, do you realize? I started with chloromethane, but I ended up with ethanoic acid. So this is how you achieve your step up. Okay? Now, I've used chlorine as an example. Now, this reaction also works if it had been bromine. All right, CBr also can. All right. Now, so far you realize that I have shown you reactions where in the step, you basically involve two molecules colliding. So take, for example, the OH minus, okay, formed a new covalent bond with carbon, right? Delta plus, delta minus. Now, this is basically two molecules colliding together. Okay? Now, this actually forms a transition state. Okay, never mind, let's just show like that. This actually forms a transition state. Now, the dotted lines indicate that the bonds are forming and breaking. So this is a transition state. So whenever you see something like that, it indicates a transition state. And of course, the transition state is very, very unstable. It will quickly form the product. Now, because it involves two molecules colliding, this is called SN2. Okay, N is for nucleophilic, S is substitution. So it's nucleophilic substitution where two molecules collide together. Now, if we were to draw the energy profile diagram, this will look like just this. All right, this is where the transition state is. Remember, transition state is very unstable. It's at the maximum of the energy profile. Okay. Now this is called SN2. It involves two molecules colliding together in the mechanism of the reaction. Okay. Now we're going to move on to a different mechanism, but it's still nucleophilic substitution. And this time around, I'm going to be using skeletal formula. So this, okay, this is what I call a tertiary halogenoalkane. Why is it tertiary? Because if you look at the carbon, there's delta plus, it's connected to three other carbon atoms. Now, in a tertiary halogenoalkane, what happens first is this. The CCl bond breaks first, and this is a slow step. So it forms a carbocation intermediate. All right. Only after the slow first step, then the OH minus or whatever your nucleophile was will come in to react with it. Okay. So this, you realize in a tertiary halogenoalkane, in the slow step, there is only one molecule involved in the slow step. This is different from just now. Just now, you had two molecules colliding together. This one only one. So this is called SN1. All right, so these are two different mechanisms. Now, why are there two different mechanisms? Obviously, it has something to do with the carbocation intermediate. We have mentioned carbocation ion when we talked about alkenes, right? Electrophilic addition has carbocation ions being formed. So similarly here, why is there SN1 for this particular halogenoalkane? If you look at this, a tertiary carbocation is more stable, right? So because it's a tertiary halogenoalkane, it will undergo SN1 because it forms a more stable tertiary carbocation, okay? So this mechanism is preferred by tertiary halogenoalkanes. Now, if you were to draw, okay, the energy profile diagram, it looks like this. This is what the energy profile diagram for SN1 looks like. Where is the intermediate? This is the carbocation intermediate. Okay. Okay, so now we already know there are two mechanisms. So now we need to know, okay, so which mechanism is used for which halogenoalkane? So we start with methyl, the chloromethane. Chloromethane is the smallest, right? CH3Cl, small. Then we go to the primary halogenoalkane. So primary halogenoalkane means like that, right? The delta plus carbon only has one carbon attached to it, so it's primary. Then we have secondary halogenoalkane. Something like this. Again, the delta plus carbon has two carbon attached to it. Finally, last one, we have the tertiary halogenoalkane. Okay, where the delta plus carbon has three other carbons attached to it. Okay, so I'm using skeletal formula for the rest. Now, so obviously, whether it goes through SN1 or SN2 depends on the stability of the carbocation, right? So we need to think of what's the carbocation formed. In chloromethane, the carbocation will be CH3 plus. This is very unstable. CH3 plus is very unstable. In the primary halogenoalkane, it will form a primary carbocation, which is also unstable, right? Secondary halogenoalkane forms a secondary carbocation, which is moderate stability. Finally, the tertiary halogenoalkane forms a tertiary carbocation, which is very stable. Meaning, chloromethane and primary halogenoalkanes would not do SN1 because the carbocation intermediate will not be stable. Therefore, SN1 is not favored for these two. So it will be mainly SN2 instead. On the other hand, tertiary will be mainly SN1. Finally, the one in the middle could be SN1 or SN2. Okay. So this gives you a hint, a flavor as to which mechanism is preferred based on the halogenoalkane you had started with. Okay. And with that, okay, I think this is a good juncture to stop whatever we are doing today so that you can slowly internalize what we have said today about nucleophilic substitution. So today you have basically done a few examples of nucleophilic substitution of halogenoalkanes. And I hope you realize from this that halogenoalkanes are actually very, very versatile organic compounds. They allow you to start making a variety of different functional groups just based on the principles of nucleophilic substitution. We have also seen two different mechanisms for nucleophilic substitution, which you should be familiar with, and you should know which halogenoalkanes would prefer which mechanism. Okay, so with that, I think we will end our lesson today. Thank you.